Hey, thank you everybody for coming. Thank you for Artem for inviting us all. And it's a pleasure to introduce Claudio Procesi from the University of Rome, La Sapienza, who is going to talk about equivariant tensor polynomials and their identities.
Okay, push. Next. Okay, so this actually is an evolution of the classical theory of Hermann Weyl, Schur, the so-called first and second fundamental theorem for classical groups. And what I want to do is to discuss a new form in which this first and second fundamental theorems appear. Okay, go ahead. So first fundamental theorem is a theorem describes generators of some proposed algebra invariants. One has a group acting on a vector space, take the algebra invariance and want to describe the generators. Second fundamental theorem is a theorem describing the relations. And what I will do, I will restrict to characteristic 0, the linear group, and some very new representation. It's possible perhaps to extend the positive characteristic due to work of Donkey and Zubkov, but for the moment I have not tried. Okay. So the first formulation of this theorem, which probably all of you know, I will go very quickly, is you have the action of the linear group on several copies of the vector space and several copies of the dual space. In this case, you see one can interpret in terms of matrices, and it's like if the linear group acts on a pair of matrices by the formula which is at the bottom, and then you have the multiplication of these matrices, which is invariant, and then next. And then you see that the invariants are just the entries of the resulting H by K matrix, image of this map. And the second fundamental theorem tells us that the image is the variety of matrices of rank less or equal than D, and the ideal, which defines the subvariety, is generated by the determinants of the D plus 1 times D plus 1 minors. Next. So the point is that this theory can be formulated in several different ways. And in fact, one basic way is to use Schur-Weyl duality, which tells us that if you have a vector space, a tensor power, and then you have the action of the linear group and of the symmetric group, which are given by these two formulas, 1 and 2. And okay, next. And so the second fundamental theorem in this case is, no, the first fundamental theorem is that these two algebras are each the centralizer of the other. And the second fundamental theorem is, next, that if you have the mapping from the algebra, the symmetric group to the endomorphism of tensor space, which are given by the previous formula, the kernel of this map is non-zero only if the dimension of V is less than H. So the dimension of V is less than the power H. And then in this case, the kernel is the two-sided ideal of the symmetric group algebra generated by any anti-symmetrizer on D plus 1 elements. Next. So here, as I say, this is the group algebra of the symmetric group, and the epsilon is the sign. And of course, the symmetric group in D plus 1 elements can be embedded in several different ways into a symmetric group on each element. So this is, of course, very classical and related to many ideas in representation theory. Next. So there is a third not as classical, but still by now quite classical way of interpreting these theorems. In this case, the basic representation is the direct sum of h copies of the endomorphism algebra, of the matrix algebra, of linear maps, and under simultaneous conjugation by the linear group. And then you want to describe invariants of this action and the generators and relations. Next. So in characteristic 0, one can restrict to study multilinear invariants by classical methods. And then the space of multilinear invariants of M endomorphism is identified to the space of, to the centralizer of the linear group acting on the tensor power, which of course is also identified is spanned by the symmetric group by the previous theorems. I will denote it by this symbol. And of course, it is spanned by this function. So associated to each element of the symmetric group, you have the trace of this inverse of this element times this tensor product, which in fact is given by decomposing sigma into cycles. And then we have the classical formula, which I think is due to constant, the formula number 4, that you have products of traces of these monomials associated to the cycles. Next. Now, the point is that one has to generalize this setting to equivariant maps. So let me just remind you what is the notion. You have two vector spaces, and you have a polynomial map is just a map which is in coordinates is given by polynomials. And then such a polynomial map is G equivariant if you have an action of G on both spaces, if the polynomial map commutes with the action. Next. So one, again, a fairly classical result is that one considers not just invariants of matrices, but equivariant polynomial maps from M tuples or H tuples, in this case, of matrices to matrices. And this is a non-commutative algebra by multiplication of the values, since n v is non-commutative. And then the theorem is that this is generated over the ring of invariants by the coordinates. So this means that these equivariant maps are linear combinations of formal expressions of this type. You have traces of monomials times some monomial. And this formal expression can be understood as a free algebra with trace. Next. Next. So just a quick tour on algebras with trace. So this is the language of universal algebra. Well, one can define a trace in an algebra as just a map, a linear map, which satisfies this various obvious conditions which are satisfied by the usual trace of matrices. Then you have the image, which is a subalgebra, we call the trace subalgebra. And we do not fix a priori the value of the trace of 1. And then we have a category where the maps are trace compatible homomorphisms. And as I already mentioned before, algebras with trace admit free algebras. Next. So the free algebra is just a free algebra on the variables x, this fx, and then you add formally the traces of monomials. But then, of course, you have to understand that the trace of a monomial depends on the monomial up to cyclic equivalence. So in some sense, you're adding monomials up to cyclic equivalence as commuting variables. So then, and then of course, the algebra just generated by this trace monomial is the trace algebra. So a second fundamental theorem consists in understanding the relations or the trace identities, so the expressions which vanish whenever evaluated to D by D matrices. And this was done by Razmistov and myself many years ago. Next. And so the trace identities form a T ideal. So it means some stable under substitution of variable. And next. And the remarkable theorem, as I say, by Razmistov and myself, is that this ideal of trace identities of D by D matrices is generated by the Cayley-Hamilton identity and the identity trace 1 equal D. So you have to fix also a trace of 1, otherwise there is still a theorem, but I don't have time to explain what happens. Next. So how do you define the Cayley-Hamilton identity as a formal trace expression? You have to express, first of all, the coefficients or characteristic polynomial in terms of traces, and these are given by this formula 5. And here are some examples. So they give you the various formula for the coefficients or characteristic polynomial, and then you can define the characteristic polynomial as a symbolic expression. Next. So you define it this way. This a priori is just an element of the free trace algebra with in one variable. And here are some examples in the CH1, CH2, and CH3. Next. So the Cayley-Hamilton theorem, of course, says that the formal polynomial vanishes when evaluated in D by D matrices. So it's a trace identity. Next. And then, of course, next, we have that this generates all identities. Next. Okay, so the T ideal generated by the Cayley-Hamilton identity and trace 1 equal D is the ideal of all identities of D by D matrices. And this can be a starting point for some theory with the theory of Cayley-Hamilton algebras, which there is quite a literature by now. And I have 2 recent papers in this theory. Next. Okay, here are some further formulas. This is the polarized form of the Cayley-Hamilton identity. And you can see that this is just associated to the anti-symmetrizer. So the fact that the Cayley-Hamilton identity vanishes is the same thing as to say that the anti-symmetrizer on D plus 1 element vanishes for a vector space of dimension D. Next. Okay, now I will go a little some more slowly, since this is a new material. So I will talk about tensor polynomials, equivariant tensor valued maps, and tensor fundamental theorems of invariant theory. Next. So what we are studying now are polynomial maps. So we have k tuples of matrices, the source of the map, and the target of the map is the tensor power of D by D matrices. And both of these spaces are, of course, linear representation of the linear group. And here I work over Q for simplicity. And so it makes sense to study the maps, the polynomial maps between these 2 spaces, which are equivariant under conjugation. And since the target algebra is a non-commutative algebra, then this space of equivariant maps forms some non-commutative algebra using the algebra structure of the tensor power. Now, the simplest such equivariant maps are sort of what we call tensor variables. So you map x1, xk to the variable xj, but placed in some point of the tensor power. So you put 1, 1, 1, 1, 1, tensor 1 there, then xj, and we call this a tensor variable. And then, of course, you can, out of these tensor variables, by multiplication and linear combination, you can generate an algebra, a non-commutative algebra, which we call tensor polynomials. Next. Now, this notion I learned from a physicist in quantum information theory. I have not seen it before. And because, of course, in quantum information theory, they study operators on tensor power and interpret in terms of some quantum computer operations. Of this, I don't know very much, but anyway, I learned this. Okay, next. So here is an example how, starting from the Amitsur-Levitsky identity for 2x2 matrices, if you start to sort of insert the tensor elements, you have, for instance, this other expression, the second expression, which actually turns out still to be 0. This is not exactly the same. It's not really a consequence of the Amitsur-Levitsky, but it's, in fact, it is 0 also, this one. But if you instead you split the variables by putting 3 together and 1 separate, then this is non-zero. And if you keep splitting, it's still non-zero. So from the alternation of these various things, sometimes it's 0, sometimes it's non-zero. And the next thing I want to do is to explain what happens in general. Next. So in general, of course, we can define tensor polynomial identities. They are, you take the free algebra and you take the tensor power of the free algebra. Essentially, this is the tensor polynomials. And then you can evaluate in any algebra, and it makes sense to say that some formal element is a tensor polynomial identity. It's just a formalization of what I said before. Next. So the first thing we tried to do with Felix Huber was to understand what are the fully antisymmetric tensor polynomials, which are identities. So how do you define a multilinear fully antisymmetric polynomial in k variables? You split the k variables in groups, x1, x2, and then you take the tensor product of these monomials, and then you antisymmetrize the whole thing. So the previous example was an example with k equal 4, in which we have split it, sometimes we have split it in 2 parts, in 3 parts, and so on. And then this gives you some fully antisymmetric tensor polynomial. So the issue is which one of these tensor polynomial identities for d by d matrices. Next. Okay, so well, one can assume that these are numbers in which you decompose a partition. So it's a question about a partition. Which partitions give you tensor polynomial identities and which do not give you tensor polynomial identity? So the statement is this, that such an expression is not a tensor polynomial identity for d by d matrices. First of all, you have to have that k is less equal than d squared. And this is obvious because any alternating function on d square plus 1 variable on a vector space of dimension d square is 0. So you have to have this. But then the two conditions that if you complete this partition by adding a bunch of ones, this must be a refinement of the partition of d square, which is formed by the first d odd integers. And this is really related to the cohomology of the linear group. I do not have the time to give you the proof, but which actually is somewhat interesting because it uses some interesting function which is called the Weingarten function. Okay, next. So, but we do not have just tensor polynomial maps because also you can, as equivariant maps, these are certainly equivariant, but you can also multiply by invariants, and they give you trace tensor polynomial maps. And then also the full algebra equivariant maps is even larger, the equivariant tensor polynomial maps, since, as you will see, contains also the sort of constant polynomial maps, which are permutations. And each one of these is an algebra and a multiplication, non-commutative algebra, and it has some extra structure because if you take any map, tensor polynomial map on n tensor and another one on m tensor, you can tensor multiply this. So we have a refined object, a sequence of algebras and some tensor products among these algebras. Next. So here's again an example, the example we had before, which is a tensor identity. Here is an example of a trace tensor valued map which vanishes on 2 by 2 matrices. This so if you look at it, it looks a little bit like the Cayley-Hamilton identity because you have some sort of quadratic term, then a term multiplying the trace, and then the determinant. But then, of course, it's sort of displayed as a tensor map. And this is what I will try to explain next. Next. So how do you understand tensor, the general form of equivariant maps? So this is actually not very difficult because if you have an equivariant map with values in this tensor power of matrices, then you can associate to this an invariant by introducing n extra variables, y1, y2, yn, and then defining the following invariant, which now is an invariant of the first kx variables and of the ny variables by just taking the trace of the equivariant map, which takes value in this MD tensor n, multiplied by this map with these new variables. When you take such a trace, of course, now this becomes a scalar value function, and this is clearly invariant. So it's an invariant canonically associated to the equivariant polynomial map. On the other hand, since the trace form is non-degenerate, it's easy to see that once we know this invariant, we can reconstruct the equivariant map H. Next, I'll give you some examples next. So what we do, we easily see that there exist some monomials, and such that if we multiply this by yi and we set this zi, then this invariant can be expressed in this form. It's sort of an invariant in terms of this variables zi. Next. So here are some examples, because this thing, one can learn it only by playing it with an example. So suppose that the invariant associated to H has this form. So here you have y1, y2, y3, and then x3 is 4, x1, these 6 variables. Now, then you construct this sort of variables. So with so z1 is m1 times y1, z2 is m2 times y2, and so on. And then you see that by just playing with this thing, that the final formula for H is the one at the bottom, which is the permutation 2, 3, multiplied by this tensor monomial. So you see, in this particular case, this Equivariant map is not a tensor monomial, but is a tensor monomial multiplied by a permutation. Next. So in general, of course, one can do this by the usual decomposition into cycles, and then one has this formula 12, which gives H as the trace of some product of traces of monomials times the permutation sigma minus 1 times a tensor monomial. So this is some kind of decoding the previous formula, associating to this invariant then the Equivariant map. So any Equivariant tensor polynomial map is a linear combination of maps given by this formula 12, which can be viewed as a first fundamental theorem for tensor-valued Equivariant functions or matrices. So this is basically an easy theorem. Next. So one uses actually this very simple fact on a symmetric group, that if you decompose the set of indices into two parts, two disjoint parts, then you can sort of split the cycles in the sense that every permutation can be uniquely decomposed as the product of 3 permutations, where the first permutation is made of cycles which contain exactly one element of A, the non-trivial cycles. The second permutation is formed by cycles which permute only elements in B, and the third permutation permutes only elements in A. So this is basically an exercise that you can decompose a permutation in this way. But then once you do this, then it's easy to make the interpretation of the previous formula. Next. This is the interpretation. You want to understand this formula 13. Now you decompose the indices 1m into A, B, where A are the first K and B are the other one, are the indices for Y1, Yn, if you want. And then you split the cycle, and then you have the explicit formula, where these things come. So this is tau 3, then this part comes from tau 2, and this part comes from tau 1, this monomial, tensor monomial. So this gives you a precise, explicit algorithm that you can implement in the computer to associate to any permutation, and but interpreted using some variables x and some variables y into as a equivariant map into the variables x. Next. So here is an example. Take this permutation, and now you can interpret it either as an invariant in this way, or as an equivariant map in this way, or an equivariant two-valued tensor polynomial map, or three-valued, or as an operation in the fourth tensor power, then becomes just the permutation itself. So you have these four interpretations of the permutation as a tensor valued polynomial map in the scalars, in the one-dimensional tensor power, in the two-dimensional tensor power, in the three-dimensional tensor power, and the four-dimensional tensor power. Next.
Claudio, I know you started about 10 minutes late, but I guess we should probably be wrapping up in about 5 minutes from now. That's possible?
Well, I will not say very much, but okay, go next rapidly. Next. So next, I will forget this.
Sorry, I didn't mean to
I want to go to the next. Just to show you some identities. So, in order to develop the second fundamental theorem, you start from the basic identity, the anti-symmetry is equal to 0, and then you split these variables in various ways, and you get various identities. Next. Okay. So here is a way to do it. You split the variables into x's and y's, and then you get some formula 18, which I'll give you in the next transparency. Next. Okay. Next, this is not so important. Next again, I just want to give you the formula. Okay, here are the identities that you get from this method. Here's for d equal 2 and k equal 1. So in two tensor variable and in dimension 2. In dimension 3, you have this identity here. In dimension, and this other identity for three tensor values. Next, I will give you the general formula. So a general formula is this. You define this tensor polynomial as a sum of all this tensor power in which you split in all possible ways. And this is an example. And then using this tensor polynomials, you get the formula. Next. So this is the type of identity which corresponds to the Kelly-Hamilton identity. So you see you have a partial anti-symmetrizer times some kind of tensor Kelly-Hamilton identity. Next. Okay, so the first theorem is that the relations for equivariant tensor polynomial maps are all consequences of these D+2 basic relations. So they are consequences in the sense of T ideals, but of T ideals in this tensor algebra. Next. So the idea is that you have a sequence of ideals in these various tensor powers, and then you define a T-tensor ideal by something which is generated. If it is a tensor ideal, if it has the property that the obvious property that when you multiply, that is a T ideal, and when you multiply, you tensor multiply, these things are still in the ideal. So this is sort of, you have this notion of tensor T ideal. So the tensor T ideal is generated by those previous, this D+2 identities. Next. Okay, so this is just what I said. This ideal of tensor identities for D by D matrix is generated by these basic relations, and trace of 1 equal D. This generalizes the Cayley-Hamilton identity theorem. Next. So, but then one can go further, because there is a further operation here, which is the partial trace, which is given by this formula. You take the trace of the last matrix variable, and so you pass from n tensor to n minus 1 tensor power. So this is sort of this is also a symbolic operation which is compatible with the evaluation. So it is clear that if you have a tensor identity, then also the symbolic trace is a tensor identity for D by D matrices. And we can exploit this to further reduce the generators. Next. The point is that when you take the partial trace of one of these are the basic tensor identities which I gave you before, then this is 0. But if you multiply by 1 to the n minus 1 times x, then you get the next tensor identity. So these various tensor identities for various powers of tensors are all related one to the other by this partial formal trace. So this means that they can be deduced from using this formal trace just by using by the one associated to 0, which is just the anti-symmetrizer. So this is in fact the final deduction that the ideal of relations of tensor polynomial maps is deduced under the operations of substitution, tensor product, and partial trace, all from this anti-symmetrizer. This is sort of a final theorem. Next, I think I'll just thank you. Okay, so, this is just a formalization. One defines a T-tensor T ideal if it's stable under T. And then, as I said before, in the final form, the ideal of identity is generated as a T-tensor T ideal by the anti-symmetrizer, and trace of 1 equals D. Next, I think I'll just give you thanks for the attention. Okay, I think I've stayed into 5 minutes. I don't know if you understood because I was running very fast. But anyway, this is all.
Thank you, Claudio. I guess, do we have time for questions, Artem, or do we want to move on to the next talk and do all the questions at the end?
I think we will have some time for questions, okay?
Okay, good. So I think Fabian was the first person to raise a hand there.
Hello?
No, sorry, I was just looking for a button to clap and thank the speaker. Sorry.
So anyone have any questions? I can't tell the difference between raised hands and virtual claps.
I do not hear well. I don't know.
I guess if you have a question, I guess shout out because I can't see virtual hands anywhere.
Well, I have some question.
Go on then.
Okay, and so my question is the following one. So here you used the notion of trace, which is satisfies certain properties, I guess it's associative because here everything is associative and commutative. Do you know anything did anyone try to consider a similar conception of trace for a non-associative case when we actually do not require for trace to be associative, or maybe even not commutative, but maybe it should satisfy some other conditions? So my question is motivated by the following thing. So if we consider some non-associative algebra and we consider the action of group-based automorphism, then we have operators of left and right multiplication, and we can take their traces and their invariants. And by doing it, we can construct some invariants, maybe all of them, maybe not, we don't know in general. But as a result, we get traces which are not in general neither associative nor maybe commutative. And so I'm asking, maybe, do you know anything? Maybe somebody tried to create some general theory of identities with traces in non-associative case.
Well, I'm not the right person to ask because I never worked on non-associative. Except I worked only on Lie algebras. The only non-associative algebras on which I worked is Lie algebras, and in that case, of course, you have the trace of add, which is basic because you have the killing form and all these things. But usually the identities of Lie algebras, as far as I know, are quite complicated objects to study. And so I do not have, and the other type of algebras, I just have no idea.
Okay, thank you for your answer, and thanks again for your beautiful talk.
Okay.
Thank you, Claudio.